This conference will now be recorded.
So once again, good morning, everyone, and thanks again for joining the second session of our workshop on Monte Carlo Simulation. As yesterday, we will be having the session for around 1 hour, and then post that, we will be taking your questions. If you have any question in the meantime, please type the questions in your chat window. We will take it up one by one at the end of the session. And as I have requested earlier also, I'll request everybody to be on mute and let the speaker speak. At the end of the session, when we are taking Q&A, we will, as I said, we will take the questions one by one serially. And at that time, if you want, you can have a small discussion, you can unmute and discuss, but all other times I'll request you all to be on mute. Thank you. Yes, Rupal, please, if you are ready, you can continue with the session. Thank you.
Okay. So it was yesterday that we saw that in Monte Carlo simulation, we are actually running random. We are taking a random variable that was epsilon, and that was based on the underlying assumption that all the stock prices or all the indices as well, they follow normal distribution. So we were taking an inverse of normal distribution of any random number, and we're running the simulation. As we also discussed yesterday, that it's a mathematical model. It's not a physical model. We also discussed that physical model is something, as an example of an airplane that I showed to be very honest, a bad picture of an airplane in a windmill, and the airs are crossing through it. So yeah, myself being an aerospace engineer, probably I have already seen that windmill also performing. So that was an added advantage for me to clearly understand how physical simulations work. So that was about physical simulation and mathematical simulation. Of course, we took an example also of a ball dropped off, and then how Newton's equation help us simulate that model of a ball dropped off, and then what maximum height is coming up, and those sort of details. Then we of course saw the stock price simulation. We saw that this is the basic equation of stock price simulation. It can be one step, two step, n step. So when we say it can be one step, two step, or n step, I think what we did yesterday was we took 4 steps in each day and total of 22 days. So effectively, we will call it almost 88 steps in between, right? I will just show it in the Excel also. That was 0, 0.25, 0.5, 0.75, and 1. So 4 steps in each day, and the total of 22 days, effectively making it around 88 steps. So the row number 107, 101, and if you subtract this, whatever, 12, it will be around 88, 87 to 88 steps in between. So we saw that our stock price, starting from 100, it is crossing all these numbers. So at each step there's a price. At each step there's a price, and finally we reach the ultimate price. That is a single price that we have. So basically there are so many steps involved, therefore we call it more than one step Monte Carlo simulation, which is multi-step Monte Carlo simulation. There is another way that you don't have these steps, so you directly jump from 100 to the last price. That's also another way. There's no problem if there are no steps, no such simulated prices in between, and at the end of the day you have only one price. So it depends on what exactly do you need. Let's say if you want to do a valuation of an option, and if it's a European call option. So in European call option, we are only worried about the price at the end of your period. Final. Nothing in between. We don't want to understand, or we don't want to know what is happening in between. So we don't need these set of prices, right? We don't need this set of prices when we are doing a valuation of a European call option. We can simply go to this price and take whatever the payoff is, and based on that, calculate the payoff, take the average of payoff, and do the option pricing. We'll see if time permits today we can see it or not. So that is a simpler form of Monte Carlo simulation, a one-step Monte Carlo simulation. The one which we are talking here, the one-step Monte Carlo. Just in one go, you apply the equation, get a price, that's it. And if you run 1000 simulations, so you will get 1000 end prices. End prices means price at the end of the period, that's it. Whereas in n-step Monte Carlo, at each step, like the 88 steps that you got 88 prices in between. Now also, we saw that whenever you just change your Excel, your graph is changing. This series keeps on changing. This series keeps on changing, right? This series keeps on changing means these set of prices keeps on changing because of our random variable, because of our this norm inverse dot rand, this random variable. This is leading to the overall change in price of the stock. Okay. So these things we understood. Now today, what we'll do is we will see the exact implementation in Python. Okay. Now coming to Python, I think we also answered some of the crucial questions yesterday, like why Python, why not R, why not in Excel only? And we clearly understood and answered that Python is the latest language that is there in the market, and probably we need to learn that. Now at our institute, what we are trying to do is to make all of you, I mean those who of course join the session, join the course, make yourself acquainted with the best of the practices which we could implement in Python. So if you see, when you start, let's say if you type in Google the best way to learn Python, so they will clearly take you to Jupyter. That is the interface. So to those who are laymen in the language, Python is a coding language. We write it. The way we chat, the same way we write the code also. Okay, like the way you write whatever it is, the same way you write the code also. So you need some place to write the code, right? You need some place to write the code. The place where we write the code is called an interface. Okay, UI interface. There are many terminologies. Now there are multiple interfaces in which you can write the code for Python. The easiest way is to do it in Jupyter. Okay, the easiest way is to do in Jupyter. Now who will do it in Jupyter? Anyone who is layman, anyone who just wants to start, I think they will be doing it in Jupyter. But here we start with a complete package of Anaconda. So we send you the links for like how to install Anaconda and how to install the underlying softwares of Anaconda. And then Spider is the interface. Spider is the interface that we use to write our code. Okay. So our exercise today includes that we are going to get all these prices in an array format. Okay, in an array format. So this will be like simulation 1, then something like simulation 2, simulation 3. We will run such multiple simulations and store it in a matrix format. Sorry, not matrix. Yeah, matrix format, or kind of, yeah, sort of matrix format. So in Python, it is called as data frame. One of the most used, I would say, library of Python is pandas. From where? Pandas, that is a library in Python. Yesterday I told you that we have so many libraries in Python that you can clearly use them, and pandas is just one such library. So we will use pandas library. Pandas library has a function called as data frame that is always helpful to save any data in a matrix format. Let's say if you run 100 simulations, so this 88 points in a column, and sorry, these 88 rows and 100 columns. That will be your data frame. 100 into 88. Okay, that will be your column. That will be the simulation. And if you start plotting each simulation, you will get the plot like something like that we saw yesterday. Okay. So today, let us start doing that in Python. What I will start is I will search for spider, right? And let it open first. As discussed, that this is the interface where we are going to write the code. Okay, that is the interface where we are going to write the code. It's a professional way to do it. Nothing else. It's a professional way to do it. You can do it in Jupyter also. There are other places also where you can write the code. But as I told you, that this is a professional and a better way to do it. And right from very beginning, if we are on this spider, then of course it will be easy for us if you also want to write some bulky codes or heavy codes, like machine learning codes, as an example. Let's say if you want to implement ARIMA model, that's a machine learning technique, artificial intelligence. Or if you want to implement LSTM model, for example, that's another approach to calculate stock prices. You can use all of them, at least through this. Fine. As I mentioned, that Python 3.8 is the version that we use, which is, I think, the latest one that we always prefer in our sessions, and we always are focused on writing it. So let us exactly implement what we did in Excel yesterday. Okay, what we did in Excel yesterday first. We are going to exactly implement that. I will write it as exactly multi-step Monte Carlo simulation. Okay, multi-step Monte Carlo simulation. Why multi-step? There is no clear-cut definition of multi-step, but as I told you that we have 88 steps in between. So therefore, I call it multi-step Monte Carlo simulation. Okay, I call it multi-step Monte Carlo simulation. The first step towards implementing this code is, first of all, getting the libraries. Okay, getting libraries is quite easy in Python. Import NumPy as, that is the first library. Import math as, that is another library. We can curtail also few libraries. Not that it is very hard and fast, but still I am using it. So we can clearly see how we can use NumPy as well as math, both are libraries. Otherwise, I think even if you use only NumPy, that shall be fine. That shall suffice. Using math library is not that required, but we can use both. The third one is import pandas as PD, the most critical one. Okay. That's the most critical one. That is the most critical one. Pandas is the library where we will create the data frames. And then the next is import matplotlib plot and PLT. Okay. It might be possible that while doing or writing the overall code, I might make some mistakes. I would prefer that if I make some mistakes, then probably I can show you how I am going to debug also the mistakes that we do in the code. Maybe in one go, if we don't do any mistakes, it will be all good. But if we do, then it will be good that we can clearly understand how do we debug the code as well. I don't know if some of you have done coding in Java or ASP.NET, C#, such languages. But if you have done coding in those languages, there's a very clear-cut principle that you put a debug point and clearly debug it. Whereas in Python, that is not exactly possible. It is possible if you change your, in technical terminology, the IDE. This interface is usually called the IDE. That is a very technical term, although not very much required to understand. So it depends on IDE whether they provide this functionality of debugging the code or not. Okay. Anyways, this was about libraries and writing the code. We have imported libraries till now. Now, I can always use this hash function to put comments in my code. So I'm putting this comments where I'm writing that assumption is stock price follows GBM. That is one assumption. And then another assumption is that the shock is generated within parallels of normal distribution. Okay. So these are the two assumptions. I think the second assumption is not even required to be written, but I have just written for the sake of understanding, although it's very clearly understood. Okay. It's very clearly understood. Now, what is our first step? Our first step is to write a function to get the simulated prices, right? Function to get the simulated prices. What will this function be? This function will include your drift, uncertainty, change, and altogether the final stock price. Okay, altogether the final stock price. This function will include that. Okay, so we are going to write that function directly here. Our function will include simulated and prices. Okay. Def is like defining the function. Def is the keyword that is used to define the function. So I am defining the function. Okay. The first step is to take stock price. So all these are the variables that will be required. And when we call this function at a later point of time, we will put these variables, like the value of all the, what are our variables, what are our parameters? These are our parameters, right? We will put them at the end. We will put them at the end effectively. Okay. When we call this function, but right now we will take it as it is. Stock price. I will take risk-free rate. I will tell you what is risk-free rate and why we take risk-free rate. And then volatility. Number of steps. And time to maturity. These are the variables that we take. From your yesterday's example, you have already taken the stock price as 100. Risk-free rate exactly is not, I will not call risk-free rate as drift. It is the expected return of a stock. Okay. It is the expected return of a stock. Volatility, of course, we already saw yesterday. Number of steps and time to maturity. I can understand some of you might be having like, how come risk-free rate is the expected return of a stock? Because the stock is always risky. You can't expect a risk-free rate of return from a stock. Okay. But again, there's something in option price valuation, or not exactly in option price valuation only, but also in our valuation sessions, we cover risk neutral valuation. And there's a Girsanov's theorem, Girsanov's process. I think that's very, of course, very high fundamentals, but there is something a theorem called a theorem. keep in mind that proves that if the risk is 0, then the return is the expected return, which is obvious. And if there is a risky asset, then the return will be whatever, risk-based return plus risk-free rate of return. And the theorem says that for valuation purposes, the risk-neutral valuation is equal to your risky valuation. So therefore, it is fine to take risk-free rate over here. Okay. What fine to take? This neutral valuation kind of thing here. Okay. Now, I have my number of simulations. Number of simulations. I will take it as 1 as of now. Okay, 1 as of now, just to see. Okay, we will get the result as yesterday. First of all, we will implement exactly what we did yesterday. Simulated steps is a new variable which is equal to your number of steps multiplied by time to maturity. I think by now you must have understood that your number of steps are 4 and the time to maturity is 22 days. The dt, value of dt that we took yesterday was 0.25. So the number of steps are 1 divided by dt. Okay. So that clearly gives us, let us define dt. I will just write it simply as dt. Define dt. What is dt? Is equals to 1 upon your number of steps. Okay. So if dt is 0.25, your number of steps is 4. That's what we did yesterday. Now next is define drift and standard deviation of stock to implement GBM. Okay, geometric Brownian motion. To implement geometric Brownian motion, what is the value of drift and standard deviation that we should be taking? That is exactly in our Excel column number B and C. Right? That is exactly column number B and C in our yesterday example that we took. Okay. What is drift? I'm going to introduce a formula for drift. I know that we haven't done this formula yesterday, but I think over a period of time we would have told you this. That it is actually your risk-free rate minus 0.5 into volatility into volatility. So risk-free rate minus half sigma square. That is your drift. So therefore, yesterday itself I said that I think there is a difference between drift and expected rate of return. Don't get confused that drift is equal to your expected rate of return. It is not. Clearly, it is not. Okay. And of course, multiplied by dt, the variable that we had. That is actually our drift. What is our sigma dt? I have written it as sigma dt because sigma is equal to volatility. But here we are going to take it only for the square root of dt period of time. We are not going to take it like for the whole term. So volatility is like 7%, for example. If it is 7%, it is for all across period. But here we are taking it only for the small dt period. So therefore, I have written it as sigma dt, okay, which is equal to your volatility multiplied by m dot square root of dt. Okay, that is the sigma value that you took as of yesterday. I have used m dot square root, that is the math function. I had imported a library, so I'm using this implementation of this m dot square root, just to show that how do you calculate square root in Python. How we can calculate square root in Python. As I mentioned at the start, while we were starting the code itself, I clearly mentioned that it is not required to use both NumPy and math. You can do with either of them, only NumPy or only math. Of course, not with only math, but definitely with only NumPy also it should be fine. But still, I have just used math also, so that we can use multiple libraries in a single code. Okay. Now we will get down to getting the price of stock ST as time as for time t. As for time t. Okay, getting the price of stock ST as for time t. For that, I think we have to first of all stock price T is equals to NP dot zeros. What is NP dot zeros? NP dot zeros means we are trying to create a matrix of stock prices from whatever we have implemented, like number of rows and number of columns. So what will be the shape? Shape is simulated steps that we are going to use, comma, number of simulations. Okay. As I was already saying that we have some number of rows and number of columns. Number of rows and number of columns. So that is what the matrix we have kept up for. Okay. We are creating a kind of matrix first of all for that purpose. Of course, we will be using the data frame of Pandas library. Okay. Then we will put stock price 0, comma, stock price 0, comma, stock price T is equals to 0, comma, I think you must be understanding by now what we are trying to do here is that for the 0th value, the initial most value, we are taking the plain stock price. I think it's pretty obvious also. For each column, for each simulation, the first value of stock price will be your stock price at the start. So basically, 100 is the initial first value, the 0th value as we call. You have to declare that as well, right? So this is what we are declaring here. Put a comment as well. Yes, set the price of stock. Set the initial value of stock. I will not write price, but initial value of stock. Okay. Now comes the important part of implementing the loop for iterating the price. So now it's a loop in simulation that we have to use to implement the price. So we will do it as implementing loop to iterate for price of stock. Now, of course, you will run this loop for each simulation and for each step, right? For each simulated step and for each simulation, you have to run the loop. So there will be two loops effectively. There will effectively be two loops that we are going to run. In any order, it's fine. It's fine in any order you are running. That's totally fine. But it will be two loops. Okay, it will be two loops. Therefore, for I in range 1, total number of simulated steps. Okay, for j in range 0, number of simulations. Okay, because simulated steps are the number of rows that we are going to take, and number of simulations are the columns that we are going to take. Now I will take the standard normal distribution first. Standard normal distribution that we have to put it in our prices. Okay, that we have to multiply with the sigma dt. So what will that be? Standard normal distribution is equals to, now we'll use our numpy library. np dot random dot array ndn. Okay, so basically, as I told you yesterday, that is a benefit altogether of having Python and doing a coding in Python, that you get all the libraries. So basically, numpy library already includes the standard normal distribution that you want to implement. Okay, it already includes the standard normal distribution that we want to implement. Clearly, for each, we are going to do this. Now, basically, stock price at time t I comma j. Why I am using I comma j? Because for each row and each column, there is a value, and I'm going to take out these values from the overall simulation that we are doing yesterday. Now, this will be equal to your I minus 1 value. What is I minus 1 value? The value at the top. So basically, if you are at this place, if your I is 20, then you have to take the 19th value. The previous value is somewhat we are taking and then doing the simulation, right? If you see, to calculate your uncertainty also, one of the values is E19, that is the previous day value. We have to use that previous day value as well. Stock price at time t, I minus 1. Of course, comma, the column number will remain the same. The column remains the same because it's a number of simulations at which simulation you are, third, fourth, fifth, whatever it is. But for each simulation we are running that thing. Multiplied by, again I will use the maths library, math dot exponential. Okay. Again, now what we did yesterday was we didn't implement the exponential part, and here we are doing the exponential part. Here we assume that we are doing a discrete geometric Brownian motion, and here we are using an exponential part. If we are using exponential, then it shows that we are using the continuous function. So now, of course, the question arises: Yesterday why it was discrete and today why it is continuous, because we are going to increase our number of simulations to 100, and if we increase our number of simulations to 100, our dt will be 0.01. So now if the dt is significantly small, then you have to use the formula for the continuous function. Then you can't use the formula for discrete function. So that is the reason that right from very beginning, I am implementing it in exponential format. Okay, that is the reason that right from beginning I am using the formula for exponential format. Sorry, formula for continuous format. That assuming that we take continuous expression. So that formula you can also use for discrete functions, not that you can't do it. Okay. Then comes drift. Plus sigma dt into the standard normal distribution, because our all the values already had sigma dt, and drift is something that already has dt and dt whatever it is required. So we already have that. Okay. Now we have to return our stock price at time t. That's it. Return our stock price at time t. Okay. Return the stock price at time. So that is what we have done. Now the only remaining part is to put up the variables and just see the results. I think that is the only part remaining now. Okay, we have done the implementation part as much as we can. Basically, we have implemented the loops. We have calculated the prices. So this is the key function that is required. One more thing, I think in Python, as I'm already doing, if you put a tab like tabs are put here, okay, it's a tab, space. So space considers it as a line within that function. So like if def is here, so this is within this, all these steps are within this definition only. If I've taken a for loop, two for loops, so whatever these two steps happening are within the two for loops, and this stock price t return is outside these two loops. And if I start typing here right from here, then we are out of that definition as well. We are out of that definition as well. Now what I will do is I will take simulated prices, or I will just write not simulated prices but prices is equals to, I will call that function of simulated prices. I will call that function of simulated prices. Now what will we do? What was our first function value? Stock price. So we'll put it as 100 as we did yesterday. Our risk-free rate is 0.1. I know it was drift yesterday, but let's take it as risk-free rate itself today. Our volatility is 0.07 as we did or considered yesterday. The number of steps were 4 for us. Okay. DT was 0.25. The number of steps are 4, and the number of days were 22. That was just a assumption that we made. And now we are just going to do print PD dot PD is the library for that function. PD dot data frame, PD dot data frame, and all the prices that we have actually. So this print function, here is a console that we have. Within that console, it will print all the values. So now I will be running this code, and after running this code, what we expect, as it is number of simulations are only one, we should get a series of prices, something like this. We should get a series of something like this. Let's see. We are getting it. 88 prices, 88 rows with only one column. Why one column? Because our number of simulations that we have run is only one. It is exactly like yesterday, right? As what was in Excel for only one simulation. But now here you can run 100 such simulations also. You can run 100 such simulations. It's just a matter of changing that variable of number of simulations. And let's see if we run it. See, we are getting 88 rows into 100 columns matrix. We are getting 88 rows into 100 column matrix. The 0th value for each of them is 100, and only the simulation going by is changing the values, right? So you have a series of values, series of 100 values at the 88th point. Series of 100 values at the 88th point. I hope it makes sense as to what we did yesterday. Okay. To add to it, let me put it again, number of simulations being 1, and draw a graph. To plot the graph, I am using the matplotlib.python plot library. That's the best one that I can think of, which you can use. Okay. That is the best one that I can think of. There are, again, as I told you yesterday, there are multiple libraries that you can use, not necessarily only this one. I am using Python plot. There are multiple libraries that you can use. Okay, it's not hard and fast that you use only this one. Someone who gets once adapt into this coding part, they can always search for different kind of libraries for graphs. They can draw very fancy graphs. So again, Python allows you to do a lot of things, especially in terms of simulation. That allows you to do a lot of things and get a lot of value. Okay. Again, I will be using plt.plot. PD dot, the data frame that we have. Within that data frame, the prices that we are holding. It will plot the prices. Of course, we are not just going to draw like the random graph. Now we will put a title to it. We will put a label to the axis that we are going to have, x axis and y axis. We are going to put a label to them as well. So plt.title, I will be putting it title, and our title is like Monte Carlo Simulation. Monte Carlo Simulation. Also, I will be putting the X label as number of simulated steps. And Y label as simulated stock prices. And the last to call plt dot show. Okay. I will just put a comment that to plot the graph of simulated values. That is our agenda. Okay. Now, as our simulations are 1, number of simulations that we have put as 1, we will get a graph of something like this. We will get only one graph plotted. Okay. Of course, the values are 88, and Now in the plots section, if you see, we have got a graph. Okay, around 80 steps. And then I will save the plot somewhere on desktop. One second, and I will open that graph altogether. You will be seeing only the one-liner graph. So it is something similar to what we had yesterday. Simulated prices, the number of simulated steps that we are having, which is around 88, because 22 into 4, and the each step price for each of them. As our expected return is positive, it is a increasing curve. And if I do exactly the same thing for 100 simulations, I'm going to get a graph of 100 such lines, like 100 such paths that a stock follows. 100 such paths that a stock follows. I will give you the code, and this is it. Right. This is the graph. See, there are multiple lines. So I think from what we started yesterday with the famous quote from Robert Frost that, I mean, 2 roads diverge in a wood and we took the one less traveled. Of course, that was for a human being. That doesn't fit completely into what we are trying to do today, but just to make it more interactive and more, I think, fancy, I included that quote that in that same manner, the stock is following so many paths. These are 100 such graphs or 100 such paths that a stock is following. Now, for the benefit, like which takes which stock, I mean, I think anyone who has taken a long position in this stock will always want that this is the price of the stock at the end. Okay. Someone who has taken a short position in a stock or an option in a stock with a short position will like somewhere the price to be here, the lowest one. So it depends what price you are having, you want from your stock. So the path that your stock takes is very clearly the path that your stock takes is very clearly about what is the expectation you have from the stock, and your expectation is very largely dependent upon what position do you hold in that stock. Is it a long position? It is a short position, or what kind of position? You can always change any of the variables here. The number of steps, where we have this number of steps, say 4 for us. You can increase the number of steps, you can increase the number of days, you can increase the number of simulations, and get any kind of graph. Always remember that if you increase this number of steps, let's make it 10,000, then the code will take more time to run. I'm not doing it right now because it will take a lot of time, I think 4 to 5 minutes. So as you move towards implementing the more complex algorithms, the machine that is being used should be more fast. Okay? So that is where I think when you use this machine learning algorithms, of course the machine, I mean the CPU that you are using and the machine that you are using to code it should be of certain level. Not a basic laptop can do all those kind of things. It's always good to have a better laptop. Okay. So that gets us to the end of the implementation part of Monte Carlo simulation. Now, this was a multi-step Monte Carlo simulation, whereas in option valuations, we don't exactly need a multi-step Monte Carlo simulation, especially the European call option, not the American call option, because American call option can expire anytime in between. As you know, American call option can expire anytime in between these days also. But a European call option can expire only at the end period. So if you don't have a multi-step Monte Carlo, if you just have a single Monte Carlo, that also will suffice for your European call option. Okay. So that is the implementation side of thing. I think, of course, as I told you earlier, this session is small to have that kind of implementation part seen. But if you join any of these courses, like which Ditish might of course be taking up and telling you, all these courses, we include these kind of codes and the implementation part of things like Monte Carlo simulation in calculation of option prices. And now the option is not only a European call option, it can be a binary option, it can be an Asian option. There are multiple options, a barrier option. So we always take care that we implement each of these, not only one of them, but we implement each of these overall. Okay. We implement each of these, as many as possible we can extend to the implementation of different kinds of valuation of options. Okay. So that brings us to the end of this implementation part of the overall Python. I think maybe Nitish, we can, I mean, I will stop here and I will like to see if there are any questions over this implementation part today that we have done.
Sure. Thanks so much, Rupal. Thanks once again for this wonderful session. Today, actually, I don't see much of question compared to yesterday. I mean, in fact, there is no question as such. I think, I mean, the Python implementation bit may have gone a little overboard with like some of the participants, because I don't see much of question.
So it's not a
Thanks,
question, just a
Venkatesh.
request.
Thanks for your wonderful comments. All right, sure. Somebody was saying something, please.
Yeah, so it's not a question, it's just a request that can you just forward the previous classes PPT and the Excel sheet and this Python codes, because like I don't think about many of you, but I have not been able to implement each code in my Python sheet. So
No, not of
probably
course. Of
if
course
we
not.
get this.
Of course, it would not be. Yeah. Sorry to interrupt. But yeah, I mean, first of all, again, the idea was not that like you follow and do the coding along with the session. That's not the idea. Of course, I mean, it was like more for you to look at. I mean, of course, when we have more time during our courses, and during our courses, of course, I mean, we allow you to follow and implement in during the classes as well. But yeah, to answer your other question, yeah, we'll be sharing the PPTs, the Excel, and today's Python code to all participants who have registered, and also the link to the lecture recordings or both the session recordings. So you
Yeah,
can.
thank you so much.
Yeah, you all of you will get that. So you can go through and go through the lecture recordings, and I mean, you can follow it again. I see one question has come from Akash. Okay, now before that we have a question from Manmohan as well. So he has said that he wants to know the theorem applied in calculating drift. So Rupal, would you like to take that question?
Yeah, so we have not applied any theorem, but we have applied a formula. Drift is history rate minus half of volatility square. I think
and just
a
one
lot
moment,
of theory goes beyond.
Just one moment, sorry to interrupt. Akash, we will be answering your questions as well. You have to be a little patient because we'll be answering questions one by one. So we'll take up all the questions, including yours, one by one. Thank you. Yes, Rupal, sorry to interrupt. Yeah, please continue, Rupal.
It is not a theorem, but it's a formula, first of all, that drift is risk-free rate minus half of volatility square. And now coming to like how do you derive the formula, there is a lot of theory that goes beyond it, beyond I think the time allotted to this. So we can't be, we are not in position to cover that overall theory, but it's just a formula and there's a theory to it. Okay, so basically while solving the stock price differential equation, so it goes back into that area where you have a stock price differential equation and you when try to solve it, the simplest stock price differential equation. In that differential equation modeling, when we do that modeling, it gets to the derivation part where your drift is risk-free rate minus half of sigma square by 2. And that also includes another assumption that your stock price follows log normal distribution as well. Now, as I said, that if I start going into that part, it will be too much of time that will be required. That basically a stock price follows the log normal distribution. We will see that distribution, we will implement that distribution in the equation, and that will come up to the conclusion of having that drift formula. Okay, so from there it is coming, at least I can just mention it that from there it is coming that stock price follows log normal distribution. If a stock price follows log normal distribution, what should be our change in stock price? Now to exactly do all the valuation, I think we have to, it will take a lot of time, so probably that is not a place here, but yeah, that is where it is coming from. I hope I have answered it. Nitish.
Yes, I think so. I think so. Manmohan, I hope your question was answered properly. Now moving to the next question, Akash Kumar says that, thanks Manmohan, thanks for the confirmation. So Akash Kumar says that this is a completely theoretical approach. So how to factor in the market effects? Would you like to take that question, Rupal?
Yeah. Akash, you know, I told you yesterday that, I mean, of course, again, due to lack of time, we can't implement it, but I would have shown you that if I take a Nifty option chain, what I would have done is like I would have gone to the Nifty option website. I would have taken that chain. I have taken the variables from there and I have put those variables into this code and would have given you exactly same result as what the price of option there in the website is. You know, I will take it to that accuracy level that if I increase the simulation, I will get a European call option price exactly the same as, not exactly, maybe slightly different, but very close to the price that you are seeing in website or any other market data, of course, softwares if you are using like Bloomberg, Reuters, whatever it is, from wherever you are collecting your market data. But put those variables and you will get the result, exactly the same result. And that is the beauty of Monte Carlo simulation. So it's not only, I think Akash answered it, and it's a good question really, but I think just to answer it to all, that in my classes, or of course in the classes that we have from IQ, we do that part. We show you that practically this is what is happening in market, and we are replicating it in a code and giving you the results that exactly matches the market data available. And it has happened. Sometimes it has been very, very close. The prices have been very, very close to what is there already existing in the market. Okay. Just now the question arises is like, what should be your volatility? The most key part. I think the overall, I would say that the only one variable that we are always worried about is volatility. And it should be implied volatility always. If you are doing such kind of options valuation, it should be implied volatility. Now, what is implied volatility? What is this volatility? Which volatility is the best to take? I think that is again a separate session altogether on that. That you should be taking implied volatility and how do you calculate implied volatility, and basically versus implied volatility and option prices like chicken and egg situation, like which one to take first, which one to put first. Both are intermingled so much to each other. So again, that is not That a lot of theory will go into that, but if you take it, trust me, the prices are going to be very close to the market data available with you. Okay.
Wonderful. So yeah, Akash, thanks for the confirmation that you understood again, and your question was answered. Another question is there from Amarnath. So he said that how to implement that is number of steps in for continuous price model.
I think I already started this thing that difference between the continuous model and the discrete model is very simple. If you are using a continuous model, you have to use this exp, that is e to the power of the expression part. Whereas in discrete model, which we did yesterday, it was clearly a mathematical formulation. See, we calculated uncertainty, we calculated drift, we calculated the change as addition of the two, and we just simply added it. That's it. Right? So this was for a discrete part. In an equation format, we will write the equation, we will quickly do some glimpse of change in the equation, and we'll get down to this formula. So this one is for your continuous method only, continuous approach, the differential equations that we solve. Now coming back to the point that when can we decide that we have to use a discrete model or a continuous model? Usually when your simulations are high in number or the number of steps are quite high, then we always prefer continuous model. And I think to be, I mean, honestly, it doesn't even depend on number of simulations, but only purely on number of steps. If your number of steps are 100, let's say, then of course you have to use this continuous model. Otherwise, even the discrete model is perfect for. So I think that this question also and some similar questions I understood that they go as part of theory on the implementation of this. Basically, before this we covered the theory also. Although the workshop schedules were very tight, so I had to show both the things. Therefore, I have taken this example. Otherwise, before this code, a lot of theory goes into it, wherein we derive these expressions first, and then only we put into implementation. Okay, that is where it's coming from.
Amarnath has a follow-up. Yes, I think so. And Amarnath has a follow-up question. So number of steps tend to infinity case. That's what he has mentioned in the question.
Yes, yes. So number of steps tend to infinity case is what the your continuous model will be, right? Integration and differentiation, if you see what it is. What is differentiation exactly? Making a 1 meter into two parts is not, but breaking it into multiple parts.
This side.
Breaking it into multiple parts and tending towards zero is what leads to differentiation.
Right. Yeah, Amarnath, I think, was trying to say something.
Yeah.
Yes,
so,
Amarnath.
So yeah. So in the simulated price definition in that function, if I were to put continuous steps instead of 4, what should I put there?
A high value, a high number of value, like 100, 50, that kind of value.
So that makes it discrete again. So if I were to do a continuous, I mean,
what is the difference between discrete and continuous? Continuous is like approaching towards zero. When your DT
correct.
approaches towards zero. When will your DT approach towards zero? When the number of steps are significantly high. Now, what is the definition of
so I have to keep it. I have to give a large enough number.
Yes, large enough number. Now the choice is yours. Which number you consider the large enough number? Now again, why it is the choice of yours? Because which kind of machines you are using. Is your machine capable enough to do 1 lakh? Take a number of steps as 1 lakh. Is your machine capable to do that kind of calculation? Probably for some of us it might not be available. That machine might not be capable to do that kind of simulation. So that number you have to choose. Of course, 4 is a very big number. You can put it as 100 or 1000. If you put it as 1000, what will be dt? 0.0001. Can we say that dt being 0.001 is close to 0? That's our choice and thought. But of course, as you keep on increasing this value, your dt will become small, and as your dt becomes small, of course the code gets better and the function gets more continuous, close to continuous. So from discrete to continuous, it's a journey, right? As you keep on increasing the number of steps, you get away from discrete and more close to continuous, right? If you make it 1, it's completely discrete. If you make it 1 lakh or maybe 10 lakhs, it is completely continuous. Now it's from 0 to 1 to 1 lakh, which number you want to choose. Okay. I think that answers the question, Amarnath.
Yes, thank you.
Yes, and yeah, Amarnath confirms that he has understood. Sajjan has a question. He says that today's formulas seem to be different than yesterday. Is there a specific name to today's? Yesterday was GBM.
Again, I think I mentioned it that today's formula is based on that. Today's formula is based on the fact that what Amarnath just now mentioned, that if you increase the number of steps, so you should be moving towards a continuous approach, and that is what we have implemented. And why we have implemented this? Let's say if this code is shared with you, and I only use the discrete approach, and some of you put the number of steps as 1000, then this code will not be giving that much close results. So better to write from very beginning, use the continuous function only, increase the number of steps to 1000. That's it. So that is the difference between the formula. And the second difference that we are seeing is, yesterday we already assumed the value of drift, and today we are calculating the value of drift. That is the only difference. Today we are calculating the value of drift as using this formula. Yesterday we were directly putting the value of drift. So again, a change that I wanted to show you through the code, and why this difference in the formula, and I mean how we derive the formula. As I told you, that is out of the context of this overall session, but definitely had it been a Monte Carlo full session, I would have showed you why drift is like this formula. So those are the only two differences. Rest all remains the same with the specified reasons I mentioned it. Okay.
Right. So, Sajjan, does that answer your question?
Yes, Nitish and Rupal, it does.
Wonderful. Wonderful. Right. So, there's no more question that I see. But again, just to summarize, right? So, see, basically, this was like a workshop, a very brief workshop of only 2 hours to give you a good amount of idea about Monte Carlo simulation. But said that, 2 hours, of course, is not enough to dig deep into all the aspects, right? Again, not to mention about our course, but again, in case somebody wants to do that, there are like, these are things which we go very deep in all the courses that we do. I mean, if somebody has a inclination or interest to learn all this, they can look at our courses depending on their background and what they want to achieve. They can go for a course called certificate program in quantitative finance and risk management. If they have some amount of theoretical background in quants and financial market products, they can go for a little shorter duration course of 4 months certificate program in derivative valuation risk analytics. Or if you have like a very good mathematical background, you want to learn absolute deep mathematical modeling, you can even look at a course that we do called certificate program in financial engineering. So depending on your background, you may just look at these courses. In these courses, as Rupal was mentioning time and again, that in our courses, since we have enough time, and our courses are pretty comprehensive. I mean, we go quite deep into all these aspects. So if somebody has an inclination, they can touch base with me or I mean us through our website. I mean, you can email as well. Or again, since you are receiving this emails from us with the logins and all these details of the sessions, you can even I mean, reply to any of those emails, and we can send you course details in case you get interested. Right. So that was to summarize. Other than that, I think we do not have any other questions for today. So again, to reiterate, in case anybody gets interested in any of our courses, you can always touch base with us through emails or you can call us. And with that, I would like to conclude the session. Thank you so much once again, Rupal, for taking your time and conducting this wonderful session. I mean, in a short period of span of time, you covered a lot of aspects, and I'm sure the participants have definitely benefited from it. And to all the participants, thank you all for taking your time out on this weekend. I mean, days, both days, Saturdays and Sundays, and attending the session. Hope you all benefited from it. Thanks, Vedant. Thanks to you as well. And I hope you all benefited from it, and you got a good hang of, I mean, about the Monte Carlo simulation and why it is used, and also got a good look into all these things, right? So with that, I'll conclude the session. Thanks to all of you. Enjoy the rest of the weekend, whatever is left, and have a good day. Thank you.